This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Hello everyone, this is Priyanka Raghavan for Software Engineering Radio. Today, listeners will be treated to the topic data observability. And to lead us through this, we have with us our guest, Kevin Hu, who is the co-founder and CEO at Metaplane. It's a data observability startup which focuses on helping teams find and fix data quality problems. Prior to this, he researched intersection of machine learning and data science at MIT, where he earned a PhD. Kevin has written many articles on data observability in a variety of popular as well as scientific publications. So welcome to the show, Kevin.
Such a pleasure to talk with you today. I'm a longtime listener of SE Radio, and everyone on my team also is a listener, so hopefully I can make them proud today. But such a pleasure to be here.
Great. Is there anything else you would like listeners to know about yourself before we get into the show?
I think you did a great job with the introduction, and we'll touch on this during the show, but I would love to start by saying data teams have so much to learn from software teams that if you have a data team at your company, chances are that a lot of the best practices that you have developed as an engineer could also help them deploy more effective and more resilient data for your stakeholders internally.
So let's jump into observability and some definitions before we get into data observability. The first thing I wanted to ask you is something basic, but let's start from the top. How would you define observability in your words?
Observability is the degree of visibility you have into a system. And that is the colloquial definition that we use in data observability and what software observability / DevOps observability tools like Datadog and SignalFx and Splunk have developed. And it really descends from the physical science discipline of control theory, where there was a concept called the controllability of a system. Like, given the inputs, can you manipulate and understand the state of that system? Well, the mathematical dual, the corresponding concept is, given the output of a system, can you infer the state of that system? So that is the rigorous definition from which our more colloquial definition is derived.
Why do you think it is necessary to have a view of the system, the centralized view, which everyone seems to be striving towards? Why is that necessary?
It's necessary because systems are complicated. That as software engineers, we have so many systems working independently of each other, interacting with each other, that when something goes wrong, which it inevitably will, it's very, very time consuming to understand what the implications of that incident might be and what the root cause might be. And because it's difficult to understand, it costs a lot of time for you, a time that is hard to get back, and it costs trust in the people who rely on the systems that you develop. So let's go back 10 years ago or 20 years ago when it was more common to deploy software systems without any sort of telemetry. Make a Rails app, put on an EC2 box, put a heartbeat check there, and call it a day. I'm not saying everyone did this, but a lot of people did do this. The only way that you knew that something went wrong in your system was degraded or broken performance for your users. And that is not acceptable. And over the past decade, with the rise of tools like Datadog, we have the visibility so that your team can be proactive and get ahead of breakages. That's why it's important, is because it helps you stay proactive and maintain a lot of trust in your system.
I'd like to revisit the physics definition that you gave to the first answer. So we have this term entropy in physics, which has pretty close connection to control theory, information theory. What I was wondering is how the uncertainty of an outcome, how does that relate to observability?
Great question. And observability has very deep roots in physics. We'll talk about entropy, but we can go into the other root in just a second. But entropy is the measure of the amount of information in a system, at least in the information theoretic definition. It is the number of bits, in other words, the number of yes or no questions that must be answered for you to fully understand a system. So in a very simple system, for example, a gas at thermal equilibrium in a box, you don't need many yes or no questions to fully describe that system. When it becomes more dynamic, right, when it starts turning into like your software infrastructure, you actually need many yes or no answers to understand fully the state of that system, which one is part of the reason why observability is important is because our systems tend to become more entropic over time. It's almost like the second law of thermodynamics where entropy only increases. That also applies to man-made systems, unless you're kind of pulling it back in case you had that one person on your team who is a real stickler for refactoring. And as systems become more and more entropic, the surface area of breakage increases. And that's why you need observability, or at least some increased degree of visibility, is to fight against the forces of entropy. And not all of it is under your control or your fault either. On a data team, right? For example, if you centralize a lot of data in an analytic data store like Snowflake, you can be very disciplined about the data sets that you create. But if you open that up to your end users and they start using a business intelligence tool like Looker, they can start exploding the number of dependencies on your system. So that's entropy can emerge in many different forms. But I love the fact that you brought that up because to go to observability and its roots in control theory, believe it or not, this takes us all the way back to the 17th century, I believe, where Christian Huygens, he was a Dutch physicist, a contemporary of Isaac Newton. He discovered Saturn's rings. He created this device. So he was from the Netherlands, and the Netherlands are famous for windmills. The problem with windmills, which were used at the time to grind grain, is that there's an optimal speed at which the millstone rotates to grind grain into like the right shape and size, but wind is variable speed. Right? You can't control the speed of the wind. But Huygens developed this device called the centrifugal governor, which is almost like an ice skater that when they bring out their arms, they slow down. And then when they bring in their arms, they speed up. It's the same concept, but applied to like a physical system where now using this device, the speed of the millstone is much more controlled. But fast forward a few hundred years, you have James Clerk Maxwell, who many of your listeners may know is the father of electromagnetism, right? Maxwell's equations, the four equations that govern them all. He developed control theory to describe how a centrifugal governor works. He was trying to understand, okay, like given the inputs into this spinning machine, what are the dynamics of that machine, and vice versa from observability. And that's really the lineage that we trace down all the way to today, where ultimately you have these highly complex systems that we want to understand in simpler terms, right? Highly entropic, but give us something that we can actually use to summarize the system. And that's where the three pillars of software observability come in. We've heard of metrics, traces, and logs. With these three, you can understand arbitrarily the state of a software system at any point in time, and also where the four pillars of data observability come into play as well.
In episode 455, we did talk about software telemetry. And in fact, they talked about these traces, logs, and metrics under an umbrella term now, which is software observability telemetry. In data observability, you told me about four pillars. What is that? Could you just briefly touch upon that?
For sure. Well, before that, even though data is ultimately produced by either a human interacting with a machine or a machine producing data, and that it's manipulated and presented through other machines, that data does have critical differences from the software world. There are some properties that make it so that we can't take the concepts wholesale. We have to rather use them as inspiration. With that in mind, the way that we think of the four pillars of data observability is, okay, Priyanka, if you describe the company you work at, like, what is the data? You might say, okay, well, if I have a table in a database, I can describe, like, here's a distribution, like for example, the distribution of the number of sales, right? This number has like a certain mean value, this min and max, and that here's a list of a bunch of customers, right? Here are the regions they're from, right? The number of regions, like which columns have PII. These sorts of descriptive measures are what we call metrics, right? They're metrics about your data. Then you might also say like this customers table, these are the columns and the column types, that's schema. This is the last time it was updated, the frequency with which it's updated, the number of rows. We call this metadata, like external metadata. And the reason we draw a distinction between these two is because you can change the internal metrics without changing the external metadata, and vice versa, where like the sales can change, we don't necessarily need more rows. But if the schema changes, it doesn't necessarily change the statistical properties. But then you might say, okay, but this is just one table. Data is all connected to each other. That ultimately, going back to the sources, it's a human putting a number into a machine, or it is a machine producing some data. And everything derives from some operation applied to those ultimate sources or some derived table thereof. And that is called lineage. And that's a pretty unique property to the data world, where the data comes from somewhere, right? At multiple levels of resolution, so to speak, where you can say this table is the result of joining these two parent tables, or this column is the result of this operation applied to two parent tables, or even like this one data point is the result of another operation. So it's important to track the lineage over time. And lastly, it's important to understand the relationships between your data and the external world, where your company, you might be using a tool like Fivetran or Airbyte to pull data from an application like Salesforce into your database. And ultimately, your data might be consumed by like an operations analyst who wants to understand what's the state of my process currently. And data is ultimately meant to be used. So, and logs kinds of encodes that information. So to back up a little bit, you have two pillars describing the data itself, metrics and metadata, and two pillars describing relationships, lineage and logs.
Great, this is fantastic. But before I dive deep into each of these areas, I want you to tell me about, say, the similarities between data and software observability. So listening to what you just said, I can understand that the similarity is that it lets you get to the root cause of an issue. Is there anything else?
The biggest similarity, you're totally right, is the job to be done. That one of the major use cases of an observability tool is incident management, to tell you when something potentially bad has occurred and to give you the information you need to both identify the root cause, like you mentioned, and identify the potential impact. In the software world, you might use traces, right? Like time correlated or request scoped logs. And in the data world, you might use lineage. So it does the same job there. And ultimately, it's for the same overarching purpose, which is to save you time and to increase trust in your system.
If there was one thing that you could say, which is the difference between data and software observability, is it this thing with the lineage that you talk about? Is that the difference, or are there more things?
There are more things. Just to go down some of the more common differences that we've seen, there's a common saying that you should treat your software like cattle and not pets. And, I don't condone treating, cattle necessarily, but basically treat your software as interchangeable. That if something isn't working, right, treat it as ephemeral, treat it, as stateless as possible. Just like take it down, spin it back up. You can't do that in the data world, where if your ETL process is broken, you can't just, spin it down and spin it back up and now everything is fine. Because now you have bad data in your system or missing data in your system. So you have to backfill everything that is bad or missing. So that I would consider data not like cattle, but more like thoroughbred racehorses, where the lineage really matters. You can't just kill it. Like you have to really trace everything that's been going on. And one corollary of the fact that data has like these lingering consequences is that like if there's a data incident, the negative impact compounds over time, right? Every second that passes, the amount of bad data or missing data goes up and up and up. It's so critical to minimize the time to identify and time to resolve issues in the data world. Of course, it's very like case dependent, depends on how data is used, but I think that's one really critical difference. And another difference is the absence of playbooks in the data world. So as engineers, we have playbooks to diagnose and fix issues, but in the data team, there are none. That if there's a bug that occurs, you get like some duplicate rows, it affects your churn, and then everything breaks from there. That's something that we want to change with introducing data observability and something that we think will change, but we're not quite there yet.
So those are the things that you can learn from the software observability space. That is, how can you self-heal, I guess, is what you're saying. I guess what I'm not very clear about is if there is missing data where you said you had to go back in time and, try to figure out what happened and how do you get back. How do you do that? How do you fill in missing data?
Interpolation might be an answer in certain cases. I think it really depends. Like the number of ways that data can go wrong is similar to the number of ways that software can go wrong. There's an infinite number, right? It's the whole Tolstoy quote about all happy families are the same, all unhappy families are unhappy in a different way. So if you do have missing data, for example, because your ETL process failed for a day, and one way to fix that, hopefully, is if Salesforce has their own system of record and has that data still existing, right? You can just like spin it back up and extend the window that you're replicating into your database, and then you can call it a day. If in another situation you have streaming data, let's say your users are using Segment and that is being popped into your data warehouse, or you have a Kafka stream, like an event stream, and then it goes down for a day, that you might have to do some interpolation because you're not going to get that data back unless some other system is storing it for you. So it's really case dependent, which is why it's so important to have this root cause analysis.
One last question I want to ask before we deep dive into the pillars is there a rule of thumb on how many metrics you should collect to analyze the data? The reason I ask that is because in software observability also, we find if you have too many metrics, it's mind-boggling. And then you forget what you're looking for because you're just overwhelmed by the metrics. So is there a rule of thumb that typically data engineers should have only so many, or is there no limit on that?
I think the industry is still trying to arrive at the right level. I personally like reverse engineering from the number of alerts that you as a data observability user get into your whatever channel like Slack or email or PagerDuty, where that's ultimately what matters, is what does a tool draw your attention to? And behind the scenes, it doesn't matter so much how many metrics or pieces of metadata are being tracked over time. And we found that it depends on the size of the team, but a nice sweet spot might be anywhere between 3 to 7 alerts per day at max. Once it goes beyond that, then you just start with like tuning it out, right? Like your Slack channel is already going crazy. Anything above and beyond like a handful a day is too much. Now, to go back to your question, like what does that mean for the number of metrics that you track? It means that we have to have a nice like compromise between tracking as much as we can, because like we mentioned before, like the surface area is key. Anything can go wrong, especially when there's so many dependencies, that we want to track at least the freshness and the volume of every table that you have, if feasible. That also means that if we do track everything, that our models have to be really on point. Any anomaly detection cannot over alert you, and the UI needs to be able to synthesize all the alerts in a way that isn't overwhelming and just gives you what you need at that point in time to make a decision about triage, essentially, like, is this worth my time? So that's where the quality of the tool comes in. And it doesn't have to be, of course, a commercial tool. It could also be something that you build internally or open source, but that's where a lot of the finesse comes in.
I think that is a very good answer, because I think the tooling also helps in fine tuning your way of looking at things and maybe your focus areas as well.
Right. I just wanted to draw the analogy to like a security tools where ideally your vulnerability scanner scans everything, right? It scans the whole service area of your API, but doesn't cry wolf too many times. It doesn't send you too many false positives. So it's the same balance there.
It's a good analogy that, yeah, the false positive is not like through the roof, because that's also something that you work with, right? You also tune the tool to say, hey, this is really a false positive, so don't show up next time. So then your alerts also get a little better because you work with it over time.
For sure. And thankfully, we don't work in a space that is like cancer diagnosis or self-driving cars where false positives in our world are okay. You just can't have too many of them. And you want to make sure that users, right, engineers who are actually doing the work feel like their agency and time is being respected. So if you're going to send me a false alert, at least make it something that's reasonable, that I can give good feedback into you, and then you can learn from that over time. You're totally right.
Great. So maybe now we can just deep dive into the pillars of the data observability. So the first two things I want to talk about is where you talked about metadata, which is the data about the data. Can you explain that? Give me some examples and how you would use that for observability.
The most foundational tests do describe the external characteristics of data. For example, the number of rows, i.e. like the volume test, the schema, and the freshness. And the reason this is important is because it is the most tied to the end user value. So to give you an example, oftentimes when people use data, there is like some time sensitivity of it, where if your CFO is looking at a dashboard and it is 1 week behind, it doesn't matter if that data was correct last week. We need it to be correct today. And that's actually a great example of the most common issue that Metaplane and every data observability tool helps identify, which is freshness issues, right? Time is of the essence here, where it's all relative to the task at hand, but you need to make sure that it is within a tolerable bound, right? If you need it to be real time, ensure that it's real time. If you need it to be fresh up to a week, ensure that's fresh up to a week. And the second most common issue that we find are schema changes, where when we write SQL or when we create tools, there's some assumption that the schema is consistent. I don't mean schema just in terms of the number of like the columns and the tables and their names and types, but even like within a column, right? What are the enums, what you would expect? And because there's so many dependencies, like when an upstream schema changes, things can really, really break. And this can happen through Salesforce updating its schema or a product engineer changing the name of an event in Amplitude, for example, which I've definitely done. And it's not intentional that you break downstream systems, but it's hard to know if you don't know what the impact is. And the third category of this sort of external metadata is the volume. And you'd be very surprised how frequently this comes up for a whole variety of reasons, where a table, you'd expect it to grow at 1 million rows a day, and then suddenly you get 100,000 rows. One, this is a good example of a silent data bug, as we like to call it, where how the heck would you have known? No one's checking this table all the time. And it's just very difficult to know both that occurred and what the potential impact of it is. There's a whole universe of root causes, but this happens quite a bit in production systems.
I had read in a lot of blogs and say literature about the dimensions of the metadata. I think they talked about timeliness. So would you group these characteristics of the data together and then that's what you track?
Great point about the dimensions of metadata. The really data observability descends from information quality research, like in tandem with software observability, but there's a huge, amazing literature from the 1990s and 2000s from pioneers like Richard Wang and Diane Strong that describe what does it mean to have high quality data. And they've identified, like you mentioned, many dimensions of data quality, such as like the timeliness of the data, referential integrity. And they also have identified like a nice taxonomy with which you can think about all of these dimensions and metrics. So just to step back a little bit, there are dimensions of data quality, which are really like categories of why things are important. Like timeliness as a dimension really answers why timing is important. Like, why is the data in my warehouse not up to date, right? Why does my dashboard take so long to refresh? But once you decide to measure that dimension, then it becomes a metric where if your data is not up to date, you might measure the lag between when your dashboard was last accessed and when your data was last refreshed. Or when your dashboard is taking a long time to refresh, you might understand like the latency between your ETL process and when that dashboard is actually being materialized or the underlying data is being materialized. So it's like high level concept and then how it's actually measured. And there's a whole list, like a huge list of these dimensions and measures over time. You can think of, is the data accurate? Does it actually describe the real world? Is the data internally consistent? Not only does it satisfy referential integrity, but that you can't pick data out of one table and out of another table and that they result in two different numbers. And is it complete, right? Does every piece of data that we expect to exist actually exist? These are what we think of as intrinsic dimensions of data quality, where even if the data is not being used, you can still measure the accuracy and completeness and consistency, and it still matters. But that's in contrast with the extrinsic dimensions, where you need to start from a task that the data helps drive, right? And some extrinsic dimensions might include, like, is the data reliable? Do your users like regard it as true? And that's related to how timely the data is, like you mentioned before, and is it relevant at all? Right? You can have a lot of data for like a product use case, but if you really need to use it for a sales use case, it doesn't really matter if it was good. And that is considered part of data quality.
Okay, interesting. The relevance of the data, that is an important factor. Yeah, that makes a lot of sense, which is something I think which, yeah, I guess maybe even software observability can learn from data observability.
Yeah, it's really a two-way street because ultimately they're two different roles. They do two different things. I do think, the data quality research is like very thorough, and that now it's really coming to fruition because data is increasingly used for like critical use cases, right? If your reporting dashboard is down for a day, sometimes that's okay. But if it's being used to train machine learning models that impact a customer's experience or decide how you allocate ad spend, for example, that can be costly.
We talked about timeliness and relevance of the data. I also wanted to know about in software observability, when we log data, we have this concept that we really need to be careful about PII and private data and things like that. And I'm assuming that's even more so in data observability. I was thinking about this Netflix documentary we watched, and we're collecting data and that contributes to bias and things like that. Does that play into data observability also? Can you talk a little bit about that?
There's yet another field that's emerging called machine learning observability, which kind of picks up where data observability stops. So frequently a data observability tool might go up into like the features, right? The input features to train a machine learning model. But unless you're storing like model performance and characteristics about the features within the warehouse, that's kind of as far as it can go. But there's a whole category of tools emerging to understand the performance of machine learning models over time, both in terms of how the training performance departs from the test performance, but also to understand important qualities like bias. And that is definitely a part of data quality, right? Sometimes bias can be introduced because the data is just simply not correct in some dimension, right? Maybe it's not timely. Maybe it's not relevant. Maybe it was transformed incorrectly. But data can also be incorrect for non-technical reasons. And by that, I mean the data in the warehouse and being used by your model can be fully technically correct And yet, if it doesn't satisfy some important assumptions about the real world, then it still can not be a very high quality data set or a high quality model as a result. And there's a lot of great work, including work by a great friend of mine, Joy Buolamwini, on algorithmic bias. And shout out to the Algorithmic Justice League, where facial recognition is increasingly deployed in the world, right? Both in public settings and in private settings, right? You look at your iPhone or you have to submit something to the IRS. Thankfully, she put an end to that. But let's just say that these algorithms don't work as well for everyone, right? And ideally, if something is rolled out at such a scale, we want it to work as well for one group as it does for another. So that is 100% a part of data quality, and a good example of how data quality isn't just the quality of the data in your warehouse. It goes all the way back to how it's even being collected.
That's very interesting, and that got me thinking about this other point. Could there be a scenario when if someone maliciously modifies the data, is that something that also the tool can pick up, or something built into the framework for tools?
If it affects underlying distribution, then a tool like ours would be able to detect when that distribution changes drastically. But oftentimes it's more subtle than that. These sorts of adversarial data poisoning attacks, which small changes into the input features have drastic changes to the behavior of the model, at least in certain edge cases. Oftentimes it's very difficult to detect. And I know that there's a lot of great academic research trying to address this problem. I don't want to overstate our capabilities or the state of the art in industry today, but I'd be skeptical that we'd be able to catch everything, just some of the most impactful attacks.
Okay, so it is probably in the infancy stage and where there's a lot more research happening in this area is what you're saying.
Exactly.
Also, in terms of this data observability, let's talk about the other aspect, right? We've talked about data quality, a little bit about the metrics and the metadata. And also, let's talk more about the logs, which is directly the data. Software observability, when you look at the logs, it's how the interaction between two systems. In data observability, I was reading that it also captures the interaction between humans and the system, right? Can you tell us how that is?
Whether it is a sales rep inputting the contract size of a deal, or it is a customer inputting their NPS score, or interacting with your site, data comes from people when it doesn't come from a machine. And there's humans that touch data all the way along the value chain or the life cycle of data within a company, from the data collection to the ETL system that was manually triggered, for example, to pull it into a data warehouse, to the data team writing transformation scripts, for example, in dbt, to transform it from a raw table to a metric that is actually relevant to the end user. And then it's also consumed by humans at the end, right? Whether it's looking at a business intelligence tool, Looker or Tableau, to see how these numbers, the ultimately aggregated numbers, change over time. It could be sent back into Salesforce to help a sales rep make a decision. That along every step of the process, there's a human involved. And the reason that's important is to understand the impact. So for example, if a table goes down for a day, does that matter? If it's not used by anyone, it doesn't really matter. But if it's being used by the CFO that day at the board meeting, you better bet that it's important that the table is up and fresh. And it's, the data doesn't tell you this, right? You need to have aggregated log data to understand what the downstream impact is, as well as what the root cause might be. And I know I'm a broken record about the downstream impact and the upstream root cause, but that's what it always comes back to, right? Just hearing about an incident, okay, that's useful, but it's the what's next that's important. And the root cause, let's say that the table is not fresh again. What could it possibly be? Maybe a colleague on the data team merged in a poor PR that broke an upstream table that your current table depends on. Well, it's important to know who merged that PR and what the context around that decision was. Maybe there was an invalid input in a source system someone put a negative value for a sales number and it somehow violated some assumption along the way. It's important to know what that was too. Because ultimately, yes, you are trying to solve the issue at hand, but you also want to prevent it from happening in the future. And unless you have like a real diagnosed root cause, it's difficult to do that. And because people are involved every step of the way, you need that information.
So this is what ties into what you call about the lineage of the data as well as the relationship of the data, right?
Exactly. Like, let's be super concrete now. Like, this is a table that ultimately describes the churn rate of your customers. For example, there are so many dependencies of that table, whether it's the immediate dependencies, like the number of renewals versus the number of churns over time. But then you go one level above that. What impacts the number of renewals? Well, it's the number of customers that you have at all, and maybe some event or some classification about whether or not they churn. But who determines what a customer is? Maybe that's a combination of the data in Salesforce with the data that you have in your transactional database. Oh, but who determines a customer in Salesforce? Is it someone that has already submitted a contract or someone that has, made a booking? Reality is surprisingly detailed. And I know that there was a Hacker News post from a few years ago saying, like, as you zoom in, there's more and more to discover. That is as true in data as it is everywhere else. Like, there's assumptions, there's turtles all the way down. And let me give you two worlds for a second, where you have that customer churn rate table. If it goes down and you don't have lineage, what do? Well, what people do today is that they rely on their tribal knowledge. Like, they might have, I know that this is what the parent tables and these are the assumptions that are in place. So let me check those out. Oh, but shoot, maybe I forgot something here. And I know that a colleague is working on this other upstream table. Let me loop them in for a second. And there's a lot of guesswork. They're very time consuming. And the holy grail is for you to have that whole map there for you and for you to not have to maintain it. Personally, I don't think it's possible to become 100% correct there, but oftentimes you don't need to be 100% correct. You just need to be helpful. And that's why lineage is important, because it helps you answer those yes-no questions very, very quickly. Okay,
that's interesting. And I think it also makes it kind of clear to me on why that is important, to find out the root cause and the impact. As you said, the two major things that we talked about in this chunk.
Write that on my tombstone. At my birthday, the root cause, whatever the year I die, that's the impact.
This is great. So let's just move on to maybe some of the tooling around this data observability. So can't you do all of this in Datadog?
You can, but it'd be hard. We use Datadog internally, first of all. I spend a lot of my day in Datadog, and it is an amazing tool. But as software engineers, we know the importance of having the right integrations, the right abstractions, and the right workflows in place. That you can stretch Datadog to do this. And for instance, you're monitoring the mean of a column in a table. But let's say that you want to monitor the freshness of every table in your database. That starts becoming a little bit tricky, right? And time consuming. You can do it. I'm confident that the listeners of this podcast will be able to do that. But it's much easier when a tool kind of does that for you. And let's say that you want to understand the BI impact, right? Integrate with Looker or Tableau or Mode or Sigma to understand the lineage of this table downstream. As far as I can tell, Datadog does not support those integrations. Maybe you can write a custom integration. And again, every listener here can do that. Do you really want to do that? Let someone take care of that for you. And lastly, the workflows. Like, this process of identifying and triaging and finally resolving these data quality issues have a somewhat particular workflow. It kind of varies by team because, like we said, there are no playbooks, but that's something that data observability tools also help with. So my answer is yes, you can do it, but personally, I don't think you should want to do it.
If I were to rephrase that question and ask you what would be the key components that a data engineer should look for when they try to pick a data observability tool, what would you say?
Integrations is number one. If it doesn't integrate with the tools that you have, don't bother, right? It's not worth your time. Thankfully, a lot of teams are centralizing on a common set of tools like Snowflake and Databricks, for example, but end-to-end coverage is really important here. So if it doesn't support what you care about, don't bother. And I also think that if it doesn't support the types of tests that you're concerned with, like no one knows your company's data better than you do as a data engineer. And you know the last few times that there were issues, you know what those issues were. And if a tool that you're evaluating or even considering building doesn't support the issues that have happened and you think will happen, probably not worth your time either. And the last thing is how much time, how much investment is required from you. And I mean that out of total respect, where engineers have so much on their plates, right? Like even putting work aside, right? Work might not be the number 1, 2, or 3 thing on your to-do list. It might be, I need to pay my mortgage. I need to take care of my parents or take care of my kids. And then work is somewhere on that list. And the number 1 thing on those work lists might be, I need to deliver this data to a stakeholder. I need to work on hiring. Very far down that list might be observability. So I think it's very important for a tool to be as easy to implement and easy to maintain as possible. Because vendors like me can go and shout about the importance of data observability all day, but ultimately it has to help your life.
So the learning curve should be very easy, is what you're saying. Also, one of the big factors for picking a tool.
Learning curve, implementation, maintainability, extensibility, all of these are important.
Let's come on to Metaplane. What does your tool do for data observability? Apart from the mission statement, which I've seen, but can you tell us on these things? Like you have the integrations, I guess. I'm guessing that's something that you concentrate on.
Yeah, Metaplane, we call the Datadog for data to be cute, but it plugs into your databases like Snowflake and transactional databases like Postgres, plugs into data transformation tools like dbt, plugs into downstream BI tools like Looker. And we blanket your database with tests and automatically create anomaly detection models that alert you when something might be going wrong. For example, freshness or schema or volume changes. And then we give you the downstream potential impact and the upstream potential root causes.
Your tools also, do they work on the same, software as a service kind of thing? Is that the same model?
It is the same model where teams generally implement Metaplane in less than 10 minutes. They provision the right roles and users and plug in their credentials. And then we just start monitoring for them automatically. And after a certain training period, then we start sending alerts to the destinations that they care about.
I have to ask you this question. It's not only for Metaplane, but generally for any data observability tool, you are collecting a lot of data. So one of the things we've seen with also the software observability tool is then suddenly people say, please ramp down on the data. There's this huge cost. This is big bills that need to be paid. So then we have to sort of reduce the logging. Is that something that you help with as well? Through these data observability tools, do they also help you with reducing your cost while also logging enough to know about the root cause and impact?
Well, we'll say it until the day we die. Yeah, exactly. Ultimately, we don't think that data observability should cost more than your data. In the same way that Datadog should probably not cost more than your AWS bill. And as a result, we try and really minimize the amount of time that we spend querying your database, both the overhead that you incur by bringing on an observability tool and to make a pricing and packaging model that makes sense for teams, both in terms of ultimately the dollars you pay at the end of the month, like the order of magnitude, less than Snowflake, and also how it scales over time, because we want users to create as many tests as possible, catches more errors, gives more peace of mind. And we don't want to make it so that, oh, shoot, I only want to create these 4 tests on these 4 important things, but if I create more than that, then my costs start exploding. That's not what we want at all. So we try and make a model that makes sense there.
Is that also something for the data observability space that you also give customers or tooling provides some feedback on how you can reduce cost? Is that something that will happen in the future?
You're laying out a roadmap. We are working on that. It is a tricky problem, but it's something that we're actually rolling out in beta right now, is analyzing the logs, right? The query logs, and analyzing the data that exists and trying to suggest both tables that aren't being used and could be deleted, and the tables that are being used frequently and could be refactored, but also identifying like which queries are being run and which are the most expensive. How can you change your warehouse parameters to optimize spend there? There's a lot of work for us to do in that direction. And we have all of the metadata we need to do it. We just have to like present it in the right way.
There's this other job title which has been around now for a few years, but it came up during this software observability boom phase, which is the DevOps engineer. Because if your data is not available now, you get a call like midnight or whatever, pager duty, and everything's buzzing. I'm assuming it's the same thing for data observability. Are a new set of jobs for people just doing this work?
There's a new, I guess, trend emerging called data ops, right? That is an exact one-to-one inspiration or copy of DevOps to the data world. There's an open question of how big data can get within an organization, right? Like, will there be roughly as many people on the data team as there are on the software engineering teams? There's arguments for both a yes and no. And I think that if data teams generally don't become the size of software teams, that data ops as a job might be taken on by existing roles, like data engineers, analytics engineers, the heads of data, of course. But I think at larger companies with sufficiently large data teams, we are seeing roles emerge that kind of play the role of data ops, like data platform managers, right? Data product leads, data quality engineers. This is emerging, but at the larger companies, and I've yet to see it at smaller companies.
Finally, if I were to ask you to summarize what is the biggest challenge you see in the data observability space, and is there a magic bullet to solve it?
The biggest challenge is extending data quality beyond the data team. Ultimately, data is produced outside of the data team and is consumed outside of the data team. And data teams themselves don't produce any data, right? We call Snowflake the source of truth. Well, frankly, it's not the source of any truth because Snowflake does not produce data. And being able to extend the visibility that observability tools bring to data teams, but to the non-data teams, I think is a huge challenge because it bumps into questions of data literacy. Like, does my CFO, like if I say that the data is not fresh, do they know what that means? Or when a software engineer is perhaps like making a change to an event name, and I was to say like, this is the downstream lineage, like, is that the right way to say it? So I think that is a open question, but ultimately where we have to go, because our goal here is trust. And the data needs to be trusted by not only just the data team, but literally everyone within an organization for it to be used.
Interesting. So I'm hearing trust in the data as well as maybe more learning on the key terminologies so that everybody's speaking the same language is what you're saying.
Definitely. Meeting other people where they are and not trying to, bash them over the head with terms that only make sense to your discipline. That's a difficult problem. And it's a human problem. Like, no one tool can solve it. It can only make it a little bit easier.
Yeah, this has been great chatting with you, Kevin. Is there a place where listeners can reach you? Is it on Twitter or is it on LinkedIn?
Yeah, I'm Kevin, Zenghu, Kevin Zenghu, on Twitter and LinkedIn. You can also go to metaplane.dev, try it out, or send me an email at kevin@metaplane.dev. I love talking about all things data observability. I would love to hear your feedback.
Great. I'll put this in the show notes and can't thank you enough for coming on the show, Kevin. It's been great having you.
It's such a pleasure talking with you. And thank you for the wonderful questions.
This is Priyanka Raghavan for Software Engineering Radio. Thanks for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.